Hello, everyone, and welcome to today's webinar on understanding RMS, reactive power, and apparent power. Your microphones will stay muted throughout the session. If you have questions, we will address them at the completion of the presentation using the Q&A feature of WebEx. However, you are welcome to type in questions at any time. Please send the questions to both the host and the presenter so we can respond. We are recording this session, and the presentation will be shared. Our presenter today is Mitch Marks. Mitch has an MS in electrical engineering from the University of Wisconsin-Madison. He's been with HBM since 2017, where he is the application specialist for electric motor testing. He first worked as a researcher at the university, working with traction motor testing and power grid research. Mitch, it's all yours.
Thank you, Krista. So today's topic, understanding RMS, reactive power, and apparent power, is actually inspired by a lot of questions we get when people start implementing our equipment, but I think when people are measuring power in general. So I hope this is informative. I hope it solves a lot of your problems, and for those in the future who are watching this, I hope it answers a lot of your questions. And just test out my pen. Perfect. So quick overview of the agenda for today. So we're going to start with a basic overview of power, reactive power, and RMS. So for those of you who are more well-versed, please don't run away. We'll get into the good stuff soon enough, but I think we have to start at the basics to really understand the issues we're facing. We'll look at some harmonics and electric power. I think this is where a lot of the issues we're going to see come from. We're going to look at the measurement and calculation of RMS and reactive power, and then look at some of the filtering effects and the definition of fundamental RMS. So with that, let's get into it. So I guess before we get into it, HBK does make a product. We make a power analyzer, as well as a wide variety of sensors and software. Our power analyzer is pretty unique, and it allows us to do a lot of the things I'm going to present on today. So I'll just go over some of our value statements quick and then get into the good stuff. So the eDrive system makes a simple acquisition of electromechanical signals. So we measure voltage, current, torque, speed, vibration, acceleration, I think I said temperature, CAN bus, all in one place, and we continuously record that data. So we really give you that battery to user experience or battery to wheels measurement chain. We make fast and accurate efficiency measurements. So we use a little trick called cycle detect, where we can actually measure electrical and mechanical power very quickly and give you very accurate measurements very quickly. Our system's future-proof, meaning that we can sell you 6 power channels in this little chassis, or you can buy 6 power channels today and add 3 more, add 6 more in the future, add mechanical signals in the future, and with your same system, your same software, have the same ability set. Our testing is auditable, and this is probably the main focus of today because we record all the data at up to 2 megasamples per second. We're storing all those voltages and currents, and then we're actually making our equations public and editable. So you get the information, we show you exactly how we calculated it, and that's where a lot of the examples I'm going to show today are from our software with our recorded data. So you can too if you're looking to do some of the things we've done. And then we offer feedback control systems. This is more for an automation system. But those are our main values. We have a really nice range of sensors, software, and acquisition. So now I'll jump into it. So reactive power and RMS fundamentals. I think before we can start to really understand reactive power, we have to take another look at real power. Now, we probably all remember that real power is P equals I times V, so voltage times current. And I've got a simulation on the right-hand side here. Again, this was in our software of a purely resistive or a purely real power situation. And in an AC power system, we have this sinusoidal wave. And here I have a voltage and current where my peaks line up, my zeros line up. We would say that these are all in phase. So my voltage and current are here. In phase, peaks and zeros line up. And then we look at our real power. And this is instantaneous power. So you really, to get a rational value, you need an average. But we can see that our power has a peak and a zero, a peak and a zero. It's got a frequency that's 2x our excitation frequency, but it's all positive. And I think that's the important takeaway here is that if we average this value, it's going to come out, something right around here, but we don't have any negative power swings. This is going to be in contrast to what we're going to see in a moment, because as many of us know, this voltage and this current are not always perfectly aligned. We introduce what we call a phase shift. And in my next slide here, I've introduced a 30-degree phase shift to my voltage and current. So same exact waveforms, except I've delayed voltage and time by 30 degrees. And on the bottom slide here, I just have our angle in a very static measurement. But again, as many of us probably know, motors, inductors, capacitors cause a phase shift between voltage and current. And visually here, what we see that as a delay in time between the zero cross of my current and the zero cross of my voltage. So you can think of it as a phase shift since this is a sine wave. If we went to the math, this would be sine of something plus 30. That would be my voltage, and my current would be equal sine of something. So that's the math definition. And if we look at it in time, this is a 60 hertz signal. A 30-degree shift is going to be a 1.38 millisecond delay between voltage and current in those zero crossings. So I've spent a little bit of time on that, so this will become important. I think I'm pretty consistent about using 30 degrees throughout this, so get used to seeing that number. So reactive power, what is it? Where does it come from? So we took an extreme example where we took our voltage and we aligned the voltage peak with the current zero and the current peak with the voltage zero. And this is actually a 90 degrees phase shift. So we would call this perfectly out of phase. And now let's look at power. So we just take P equals IV, and we can see that we have this negative power, positive power, negative power, positive power. And if we average this out, our power averages to zero. And you can think of this as I have some regeneration, I have some active power, regeneration, active power. We have this oscillation in power. This is going to be a really common theme today. So reactive power, at the simplest definition, is power showing up at the wrong time. It's getting to the load, but it's a day late and a dollar short. It does not go towards any real work. So reactive power doesn't do anything real. It's literally an energy oscillation. And we can see that. Again, we have that negative power, positive power. We average to zero. And the important thing about reactive power, and there's several important things, but a big one is it limits how much power can be transmitted. This current is real. This current takes up space in a power line. Power lines are rated to a certain power. So if you have a lot of reactive power, you can't pass as much real power with a given current level. So something to keep in mind. Now, I have this line here. This is one of the most debated things in science, and it's funny that it actually says that in a Wikipedia article, and I've always found it my whole career to be very true. Because in this kind of pure simulated, pure sine wave example, it's very simple. But when we start adding things in the real world, like harmonics, like unbalanced systems, like PWM inverters, we really start to see that, okay, there's a lot of frequency content here. This reactive power isn't as straightforward. We have a lot more oscillations. And we're going to discover a lot of this as we go forward in this presentation. Oh, what happened to my pen? Oh, there it's back. So on this next page, I just want to summarize what we've gone through so far. So voltage and current, zeros and peaks line up. We get all real power. Our phase is zero. Phase is 90 degrees. Our voltage and our current are perfectly out of phase. Peak of voltage lines up with zero current. We get this oscillation where our power is canceling out and we get this oscillatory power that does no real work. And in the real world, we have a little of both. So here we have a phase angle of 50 between 90 and 0, where we have mostly real work, but we have some reactive power. So we have some of that power oscillation. And this is where our jobs all get very interesting. Down here, I have a whole lot of math. I'm not going to go through this. I don't do math very well. But a colleague of mine does math extremely well, and in a couple of weeks, he's going to be doing a presentation where he'll go through this derivation in a lot of depth. He's an elegant speaker. I'll pitch that a little more at the end, but little preview. If you want the math, it'll be available in the future. I'm the picture guy. So now that we've described power, reactive power, voltage, and current, we've got these AC waves. They've got a frequency. They've got this phase difference. They have harmonics. They have amplitude. We can see that very quickly this becomes difficult to describe these things. And if we take that a step further, and I've already mentioned measuring power as an average, well, why don't we just average voltage and current? Well, if we take an average of a sine wave, our mean or our average comes out to 0. So that's not very helpful for us. However, we have this fun piece of mathematics called RMS, or the root mean square, where if we take, all the points under the sine wave, and we take every point, we square it, we average it, and then we take the square root of that average, or a root mean square, we end up with this constant value, and we get a value for both the positive and the negative. And what RMS ends up being in a sine wave is the DC equivalent of an AC wave. And this is pretty cool because this gives us a standard method to compare the amount of power that an AC waveform or DC waveform contains. Or for that matter, it gives us a way to describe the amount of power that a high harmonic wave and a low harmonic wave have. So we got a lot going on here. One issue with RMS, and it's not really an issue, it gives us a way of describing some extra physics, is that it's phase agnostic. DC does not have a phase. If you think about it, we're doing this RMS calculation on a voltage and on a current. And you might say to yourself, well, P equals IV, right? Well, we're taking this DC equivalent power. Good question. So this introduces us to our concept of kind of the power triangle. So real power, this is the one we're all familiar with. This is heat. This is rotation at the wheels. This is torque. This is speed. Produces work, measured in watts. And power is the average of voltage times current over a time period. Simple enough. Now, we just spent some time talking about RMS power. And I called RMS is the DC equivalent. So what happens if I take IRMS times VRMS? Well, we get that DC equivalent. So S is my apparent power number, or my apparent power variable, is VRMS times IRMS. We measured in volt amps, a very clever engineering name, and it's how much power there appears to be in a circuit. But we do need to consider that this does not have a phase angle in it. And I spent a decent amount of time talking about phase angle as well. Here's where reactive power comes up. We remember reactive power is that oscillating power. It's measured in volt amps reactive, another very clever engineering name. And we have a couple calculations here. So we have Q, Q's our reactive power, is the square root of S squared minus P squared. But it also equals V times I times the sine of theta. Theta being that phase angle between the peaks of our voltage and current. And if I take these values and I come over here, we have this apparent power, which is our DC equivalent, but that's not all going towards work. We have a real power, that's all going towards work. And then we have our reactive power, which is a 90-degree difference from our real power. We end up with this power triangle. And in the ideal world, our power factor angle is that phase shift. But as we all know, we live in the real world, so this isn't exactly true. But in theoretical, at the fundamental level, it absolutely is. All right, you're all experts on the basics. Now we get into the fun stuff, where the purpose of this presentation comes in. So harmonics and electric power. It's a brief background on harmonics. I'm sure you're all familiar, but if we take a square wave is the Taylor series of an infinite sum of sine waves at different frequencies. So we have a fundamental. We potentially have a third harmonic that's 3 times the frequency and a third the amplitude. A fifth harmonic, 5 times the frequency, a fifth the amplitude, 7 times a seventh the amplitude. And what we're going to find is that we find a lot of harmonics in our AC signals. And if you have an inverter, it's even more harmonics. So these are going to be really relevant things when we start looking at values like RMS. So what happens if we do that? So again, I was just working in kind of the simulation mode of our software. I took our voltage and our current from the previous section, and I added some harmonics. So I took a 60 hertz, 30-degree phase shifted current, and I added a fifth harmonic and a seventh harmonic. And you can see 5 times 60, 7 times 60. Next, for the voltage, I again took my sine wave, not phase shifted, and then I added a lot of fifth harmonic and a lot of seventh harmonic. And we can see in our example here, in the blue, I have my voltage that's got those really kind of drastic peaks in the sine wave. I've got my current that's got some shape, but not nearly as much as the voltage. And I'm going to do some calculations on these, and we're going to see what happens. So we'll start off with our instantaneous power. We'll start at the same place we did previously. So what we see is I've got my power in my aqua, and we can see that I'm just taking P is I times V, and we get this really jagged waveform because that multiplied product is following the shape of those voltages and currents. And in the black, I have my average, and down here I have my zero. And we can see that we get a lot of oscillation in that power. And if we remember the definition of reactive power, it's that oscillation in power. So we see that oscillation, and we have, again, that negative power. Here's our reactive element, that positive negative counterpart. So to really start understanding this and really start describing these things, we can see how difficult that would be. So we want to use our RMS and our average powers. And again, I can't stress enough that these oscillations in powers indicate that there's a lot of reactive power, and we're going to find that in a moment. I give away all my secrets ahead of time. So we take that waveform that we had previously, our voltage, our current, our high harmonic power, and we'll kind of break it down by what we're doing here. So we have this full bandwidth data. It was 500 kilosamples per second was my simulation rate with a 50 kilohertz filter. So this is all the glory. I don't have anything happening nearly at 50 kilohertz, but then I calculate my RMS voltage, current, power, reactive power, apparent power, and I find these graphs to be pretty boring because they're constants. But you can see we have this voltage, current, apparent power, real power, reactive power. And if I run my calculations and I measure my values, we can see my IRMS 72 amps, VRMS 412. Keep this number in your head. Our apparent power 30 kVA, real power 24, reactive power 16 kVAR, and then our fundamental phase is 0.52 radians. Fundamental phase is that phase shift between, we'll use the zeros here because those are a lot more obvious. Our voltage zero and our current zero. It's the phase shift between those two. Remember, this is 30 degrees. And we have a power factor, and we're going to define power factor as P over S. So real power over apparent power, 0.827. Now, if you remember back, we had a couple equations for reactive power, and I think we should look at those. So we have reactive power is the root of S squared plus P squared. Straightforward enough. Oh, minus. So we have 30 squared minus 24.9 squared. We get 16.9 kVAR. That's that same number I have here. Cool. That works. Then you put up that other equation. We have voltage times current, so VRMS times IRMS, times the sine of theta. Well, I've got a theta here. What if I plug this value in right there? And we multiply that out, and we get 15.1 kVAR. Why are these two values different? This is where the questions start coming. Well, this is the fundamental phase. So this is the phase just of those zero crossings. This doesn't actually take into account all of the reactive power there is, because we need to consider that V and I have harmonics. And each one of these harmonics has their own amplitude and phase. So if you wanted to run this equation, you would need to do a lot more math. So phase in theta is for the fundamental only. Each harmonic should have their own phase angle if you really want to dig into the details. Power also contains harmonics. That power, that real power we're getting, we can measure this. This does have harmonic content to it. That harmonic content is going to change that power value. Higher or lower, it's altering it. So we really do need to consider power factor as P over S instead of the cosine of theta that we're all probably familiar with. So keep that in mind, and we're going to see this theme over and over. Okay, we've addressed that difference. These are full bandwidth RMSs, at 50 kilohertz filter rate, and we're using a phase angle that's for the fundamental. That's going to be a common theme. So let's take the next extreme example. Let's look at just the fundamental. So these are those same exact signals, except now we're only looking at the fundamental. We've effectively filtered out all that harmonic content. And what we see is, if we look at the waveform itself, we can much more distinctly see that phase shift. We can see our power has that nice sine wave, but it's not jagged anymore, and we still have a little bit of reactive power, and our average power is kind of right in the middle. So this is a little more elegant, but it doesn't have as much information. And again, I run my equations, and we see these very boring kind of flat lines. But one thing worth noting is that now my real power and my reactive power are almost the exact same, and my apparent power is way down here. And if we run those exact same equations we ran last time, the exact same equations, just on data that's now had the fundamental isolated, we can see our IRMS decreases, our VRMS decreases from, I believe it was 412. So we have that big decrease here, almost 60 volts. Because our RMS has changed, our S, I times V, is now 25 instead of 30. Our power is the same, because power is that real power. We can physically measure that and average it and trust that. Our reactive power is now significantly lower. And if we look at that phase angle, that's still 30 degrees or 0.527 rads. That's because filtering doesn't change our signal in time. And now we look at our power factor and we get P over S of 0.993. So I think this is really important because this is highlighting that with the same data, we can get two very different interpretations. So standard RMS includes fundamental and harmonics. Oh, I'm too far ahead of myself. Each harmonic has its own RMS and phase. And what we find is that equation, V times I sine of theta, is dependent on V and I being calculated for the fundamental. It's also dependent on power being the fundamental power. So we have an equation in our software called fundamental RMS, where we actually remove all the harmonic content and just look at the content of the fundamental. It's similar to a THD calculation. And we find that using that exact same equation, what previously was 16 kVAR is now 2.7 kVAR. And if we line up kind of those stats side by side, the full bandwidth and the fundamental, power is the same. IRMS is slightly smaller. Now, if we remember that VRMS had a ton of harmonic content in it comparatively, 412 to 353. That big change is influencing S, and it's influencing Q. And we see this huge difference between reactive power. And again, the exact same data, but the interpretation of it's drastically different depending on how you look at your signals. Cool. We've kind of set up this theoretical example, and I showed a really nice point. But what happens if we step into the real world? And I'm sure a lot of people here are coming from more of an electric vehicle background. you're really concerned about inverters and PWM and current ripple and all this good stuff. So an inverter PWM output is effectively a bunch of square waves. And if we remember, our square waves had a lot of harmonics. So PWM really likes to introduce harmonics. A motor acts as a filter to remove a lot of them, but it's only removing them in the current. And if we remember from our last example, our voltage had a higher harmonic content, a little foreshadowing for what we're going to see here right now. So this current ripple, this voltage switching, is reflected in the RMS and reactive power, and we're going to look at that in a moment. And again, for consistency, 500 kilohertz sampling, 50 kilohertz filter. Let's jump in. So, okay, what if we take our voltage and current and we calculate power just how we always have? P equals IV, just point by point. And we start to see this power, and we got our average power. I'm going to draw a very poor straight line, so I apologize, that's ugly. And I've got a 0, an average, and my average is 32 kilowatts. Well, I have peaks here at 300 kilowatts and negative peaks at around 100 kilowatts. And we see this reversal at the switching rate. So we have this really high frequency content in our power because of the influence of all the inverter switches. And if we, again, remember back to that statement I made originally, power oscillations indicate there's a significant amount of reactive power. What we have here is very large, very fast power oscillations. And again, this just justifies that need for an RMS voltage and an average power. We take this oscillatory thing, we look at it over a single cycle of a sine wave, and we can see that this averages out to this nice clean value. Cool. Oscillations, a lot of reactive power. We need averages, we need RMSs. So we take that data and we run our calculations. And we get RMS voltage, current, reactive power, apparent power, and real power. And if we run the numbers, we get a IRMS, a VRMS. Note this 210 again. We see our apparent power is 60 kVA, our real power is 32 kilowatts, and our reactive power is 51 kVAR. Our reactive power is greater than our real power. And again, this is where I get a lot of questions, and we'll touch on some of this in a moment. Our fundamental phase, if we remember, this is the phase shift between the 0 of my current and the 0 of my voltage. So this one's not changing. And my power factor, my P over S, 0.538. Now, all of these were calculated with the exact same equations. S equals IV, IRMS and VRMS equations, Q equals S squared minus P squared. So we see that RMS is going to have a huge effect on Q. Okay, so this was the wideband. This was the 50 kilohertz example. So what if I filter this? So in this example, we take the same data, very important, this is the exact same data, and instead of a 50 kilohertz filter, we now apply a 2 kilohertz filter. And if we look at this, we can see, all right, my voltage has a lot less oscillation. My current's got a lot less oscillation. And my real power has a lot lower amplitude and a lot less oscillation. But we still have that reactive element. We still have a lot of oscillation going on, so we're not at 0. We do our calculations again, and we can see that, okay, my apparent power has come from up here down to here. My reactive power has come from up here down to here. This is a good sign. We have fewer power oscillations. And again, the exact same equations we ran on a higher sample rate. IRMS, 287, VRMS, 134, almost 100 volt drop. Our apparent power, 38 kVA, down from 60. Our real power, the same, because real power is real power. Reactive power, significantly decreased. And now we have a fundamental phase that's the exact same again, because our 0 timing is not changing. Now our power factor, our P over S, is 0.845. Exact same equations, different interpretation of the data. So this is interesting. Now, for completion's sake, let's take that a step farther. And now we take the fundamental, and I apologize, I didn't change the color of my voltage. But we can see that we have these very clean sine waves. We have this, this power that's got this nice oscillation to it. And if we do our equations, again, RMS voltage, current, apparent power, real power, reactive power, we measure our values, and we get even a little bit more decrease. So 2 kilohertz got us most of the way there, but not all the way to the fundamental. And what we'll find is the exact same equations. We've run this fundamental calculation to really isolate the fundamental RMS voltage and current. That fundamental is if everything was a pure sine wave, that would be our value. Same real power, same phase angle, but again, a lower values on RMS values, reactive power, apparent power, and our P over S value, again, has gone up a little bit. So, let's take our comparison table. Power does not change because real power is watts, it's work. We can measure real power very accurately. But RMS, apparent power, and reactive power, these kind of more interpretive results, change drastically with filtering. I mean, absolutely changed drastically. And to say one is right and one is wrong kind of matters what your job is. And it matters what you're comparing to. And when we start filtering these things, we're removing that oscillation. But the guy who's doing control development or PWM development might want all of that content because they might want to see how their switching frequency influences that reactive power. The guy in the power grid might only want the fundamental. Or if you have a model you're comparing to at 5 kilohertz, or a consumer's or customer or supplier's equipment you're trying to compare to with, a 5 kilohertz filter, you need to know these things. Because if you want to compare the 2 kilohertz filter with the 50 kilohertz filter, you're going to ask a lot of questions because these numbers are drastically different. So please just keep in mind that you need apples to apples when doing analysis, whether it's models, whether it's previous data, whether it's historic data, whether it's different equipment. If you start asking questions, you can probably start figuring out the answers to what you're looking for. So my conclusion here, reactive power and RMS are complex beasts. I don't expect anybody to walk away being an expert after this, but I really encourage you to start asking questions. And when you go to measure these events, consider what you want to look at and how much content you want to understand before you acquire data. Because if you start asking those questions, you can set yourself up to compare apples to apples or make sure you're comparing one correct value to another. Always remember that high frequencies, be it harmonics or switching frequencies, are going to introduce reactive power. They're going to introduce oscillations into the system. And naturally, I get a chance to pitch my little baby here. Because the HBM equipment records data at the high sample rate, a ton of control on the filters you apply, you can run really wideband or high filter data, or you get high bandwidth data, and then you can filter that down in the post process to figure out where you want to operate, or you can run those fundamental equations to get that fundamental values. So we give you the option to look at one or more of these values. So you really can compare to your models, compare to your customers, compare to whatever you need to compare to. Before I thank you guys for your time, I just want to mention that one of my earlier slides, I pitched a colleague of mine's presentation that's going to be coming up. HBK is having a global virtual conference, October 13th through the 15th. We're going to have a whole day dedicated to electric power and electric power testing. That we're going to feature presentations from customers, partners, and guys like myself, HBK experts. Some of the customer presentations, FEV, we're really excited about. Stanley Black & Decker is going to be super cool. Millbrook Revolutionary, EOMIS, and WEMPEC, as well as a variety of electromechanical power topics. We're going to talk about measurement. We're going to talk about problems in the industry. We're going to talk about mechanical problems. and there will be some networking opportunities and interaction. So if you want to learn more, please register. I'd be happy to give you more information as well. With that, thank you, and I look forward to all your questions, and hopefully you guys learned something. Please feel free to reach out to me on my LinkedIn here, or send any questions to the chat or HBK Direct.
Thanks, Mitch. Everyone, as Mitch mentioned, we do invite your questions, so please type them into the Q&A, share them with the host and the presenter, and we have time to respond to a few of those. I will share Mitch's presentation with everyone who's here today. In addition, we record these presentations, and you'll be notified when that recording is available on our website for on-demand viewing. All right, Mitch, someone's asking, I only care about real power. Does reactive power really affect me?
Yeah. So valid question. Real power is kind of that. It's real. We can measure it. We're very confident measuring it. So it's more actually a matter of instrumentation. If you only care about real power, you do need to consider that your instrumentation and actually the measurement of real power becomes more difficult at low power factor. So remember that P over S. That P over S is somewhere in the range of like 0.3 or 0.1 or 0.01. So these really low power factors that actually will affect the accuracy of the measurement equipment. So one way to mitigate that is you can, one, look at what the accuracy class of your instrument is at lower power factors. Our equipment lists that, so our standard accuracy is from 0.5 power factor to 1. I will say a lot of competitors just listed at a power factor of 1. We list ours from 0.5 to 1. And we have a separate accuracy class for, I believe it's 0.01 to 0.5. We can also have systems calibrated for low power factor. So while in physics it doesn't necessarily affect your real power, in measurement it might affect your accuracy. So good question, a little abstract answer. Please, again, reach out to me if you want to debate and have a conversation about that.
All right. When would I use a fundamental versus a full bandwidth RMS calculation?
Yeah, so that kind of comes down to the question of what are you trying to compare to, what are you used to, and what do you need to look at. So I don't think there is necessarily a right answer. I prefer the wide bandwidth value, so kind of that full harmonic content beast, because you always can filter down and look at individual things if you want. But you have the option to start understanding the phase shift of your individual harmonics. But I know many people will do models where they kind of filter out the switching frequency. So maybe you want the reactive power in absence of that switching frequency. Maybe you want the reactive power of the fundamental. It kind of comes down to what you're comparing to, what you've historically done, and what models you want to look at. So not a good answer, but not sure there is a good answer.
All right. Why is it that the phase angle doesn't change between the different filter rates?
Yeah. So again, if we have our current sine wave, and I'll be really artsy here, and we have our voltage sine wave, whether this voltage is a PWM or it's a true sine wave, the phase shift between the peaks is the same. So it kind of comes down to that. If you have a phaseless filter, which we can offer, you're not affecting that phasing when you start filtering down. So that's why that phase angle stays the same. But that's just the fundamental phase angle.
Okay. Well, everyone, thank you very much for joining us today. We're glad you were here. And Mitch, thank you very much.
Yeah, thanks, everybody. Hopefully speak with you soon.